Okay, I believe, I don't know if I did that or not. On yours, we need to kind of draw in the line for this first one because it is not there. So the first type of function we need to be able to identify is the constants, which is y equals 0, and it did not show up on this graph because y equals 0 is the x-axis. So I did graph it, but it was just on top of the x-axis and did not show up there. So let's draw that in there. So constant function is just a horizontal line. We're not going to do a ton with that because there's not much interesting about it. It's very, very simple. These really go down, but I'm going to go across them because I got to scroll. So this U shape that we have here, that one is our quadratic. You also may think of the word parabola. Parabola refers to the shape of the graph. So like if we're talking about an equation, we would usually call the equation a quadratic. We could call the graph a quadratic as well, but we would only really refer to the graph as a parabola. It talks about that shape, so that's why we're not using that word parabola here, but it goes hand in hand with these. Quadratics produce a parabolic graph. They're parabolas there. So with parabolas, you have x squared as your parent function. And so we should be able to identify these shapes. So when we see a graph of a parabola, we should think that's got to be a quadratic, right? And so we should be able to recognize that. Here we have a slanted line. This is a linear function. Technically, constants are also linear, but constant is just like a more specific type of function. When I talk about linears, I'm typically talking about slanted lines, ones that are not vertical or horizontal. Your parent function for a linear function is just going to be y equals x. Just y equals x. Over here we have a cubic. And it's got this sort of squiggle shape here. Now cubics, depending on what they look like, they can look more like this, where the curve is really defined and you have maximums and minimums. We're going to be dealing with shifting up, down, left, right, that sort of stuff. So we'll mostly be looking at cubics that look like this one here. Alright. The next one that we're looking at is our square root function. You will sometimes hear this called a radical, but square root's really a better name because radical could include cube roots and fourth roots and fifth roots, and their graphs are going to look a little bit different, especially those odd roots are going to look different because you see here with the square root, we start right here at 0, 0. We don't have any values below that because anything below that, like -1, -2, -3, if we try to take the square root of those numbers, we can't take the square root of a negative. So we would have our graph that looks like this here. What's this V shape called? Absolute value. And of course we've got that V shape there. Parent function is just y equals absolute value of x. One that we are going to focus on a lot in this unit because it is a function that is specifically mentioned in pre-cal that we have to cover extensively is this one here. It is a rational function. So we will look at all of these some. We will look at that one in particular a little more than the others. The other ones that we have here, we've actually already looked at quite a bit. Here we've got natural log, so this is logarithmic. And parent function, I put natural log because that's the one that we're going to deal with the most, but the parent function is whatever log base you're starting with. So you have different parent functions based on what base you have for that log. So your parent function could just be log of x, or it could be log base 7 of x, depending on which one you're dealing with, which will change what the graph looks like a little tiny bit, but it'll still have a vertical asymptote at 0, and it'll still have the same general shape. And then the last one we have here is an exponential. And we looked at the graphs of exponentials quite a bit in the first unit. So we'll continue to throw these in from time to time. We won't do them quite as much as some of the others just because we need to focus. We've already seen them. So. And so parent function is e to the x. Same thing as with natural logs here. That base doesn't always have to be e. It could be 3 to the x, 2 to the x, whatever you have. Excuse me. Okay, questions? All right, so here is the big thing that we've got to know about, and that is what do these different transformations do to the function. So I am going to pull up Desmos over here beside just to demonstrate what's happening. We are not going to be able to use Desmos on most of this because the point of a lot of it is for you to be able to know what stuff looks like just from looking at the graph without graphing it. So that is the point of what we're doing. So I'm not going to let you use Desmos on a lot of it because I want you to know without the graph. But while we're talking about it, I think Desmos is really helpful to get a picture of what is happening here. Let's just start with what I think is one of the easiest ones to see, x squared. And so if I tell this that f of x equals x squared, right? The first change to the parent function we're going to talk about is just putting a negative out front, right? Who remembers what's that going to do to the graph if I just put a negative out front? So I do negative f of x. Just going to flip it upside down, right? So this is going to be a reflection over the x-axis. And if we think about taking, like, let's say we do take y equals x squared as our, if we do have, like, let's say that we're letting f of x be x squared. So if we're talking about doing this, it would look like this, y equals negative x squared. No parentheses, just a negative out front. All right, so what happens if we put the negative on the inside of the parentheses instead of the outside? Anybody know that one? Let's see. Nothing, it looks like, right? I just put the negative there. You can see both graphs are the same. The reason it looks like that is because x squared is just not a really good graph to look at for this. Let's make this one x to the third. Okay, so x to the third right here is my original graph, this red graph. The blue graph, f of negative x, is the second graph. What happened to that graph? Sometimes I think it's helpful to like get rid of that. What? It is a cubic function that we're starting with. So this is like our basic cubic function. But when we put that negative on the inside, it's reflecting over the y-axis. It's flipping it over the y-axis. So when we had x squared, it looked like it did nothing. And that is because if you flip x squared over the y-axis, it looks exactly the same. It's symmetric about the y-axis. So if you are doing this, you're going to have the negative inside of the parentheses for whatever you're dealing with, and it's going to be a reflection over the y-axis. And there's several functions that you can't tell that anything happened whenever you do that, like x squared, also like your absolute value, because they're already symmetric about the y-axis, so when you reflect them, they don't look any different. So that's why sometimes those may actually look exactly the same. All right, let's get rid of that negative. Who can tell me what's going to happen if we add a number to the end? Up. Okay? So if I put a, let's see if it'll put a slider. They've changed the way Desmos works a little bit. All right, so if I put a plus c, you can see it's going to move it up. If I make that c bigger, it goes up higher. What about if c is negative? It goes down, right? So it's going to go up or down in whatever direction your number is. So if your number is positive, then it'll go up. If your number is negative, then the graph will go down. And that would look like this. We would just have like y equals x squared, and we might have like a plus 3 over on the end. Okay, there. All right, what about when we start putting it inside of the parentheses? Left or right? Does it go in the same direction? It's opposite this time. So if I put my plus c here on the inside, you can see it's going to go left or right. But it's going to be the opposite direction. So you can see when I have positive numbers here, when c is a positive number, I actually move to the left. So if I have a positive, it moves left. And if I have a negative, it is going to move right. So opposite direction of the way you would think that it should go. Okay, we're good there? All right, what about if we multiply it by a c here, and here this c is a number bigger than 1? It does. What do you mean by get bigger? Because that could mean several things. So let's try. We want numbers bigger than 1. So numbers bigger than 1 are actually, instead of making it wider, they actually make it skinnier. But if we think about it, instead of wide or skinny, if we think about it tall, right, it's being stretched vertically. So we will call this a vertical expansion, or depending on where your assignment comes from, some textbooks do use the word stretch. All right, so the key to it being vertical is that it's on the outside of the parentheses. And since it is a larger number, it's taking it like it's grabbing it on the y-axis and it's stretching it taller, right? Which also makes it look skinnier, right? Because if we could take me and make me like 6'5", but my weight didn't change at all, I'd look pretty skinny if I was 6'5", right? Same. So all that would really be changing was the height, but it would look skinnier, right? So if we do the same thing, if we take me and we squash me down so that I'm only like 4'10", and my weight does not change, right? I would look much wider than I do at my current height, and certainly than I would at 6'5", right? So if I have a number between 0 and 1, then if I use a number between 0 and 1, so you can see right here, like if I have 0.9, 0.8, 0.6, 0.5 right there, that is going to be what we call a vertical compression. So you're taking that and squashing it down, right? This is a vertical compression. And sometimes, instead of compression, you might see the term shrink. Now, those are going to occur whenever those vertical stretches and shrinks are going to happen when you're multiplying by a number on the outside. I haven't been writing the examples here. Let's see. For this one, it would be x plus 3 squared. That moves it left 3. Here, this would be like something like having 2x squared, and the shrink would be something like having 0.3 x squared. Okay, so the next part, if we put this C, if we multiply it, but instead it's on the inside of the parentheses. I think these are a little bit tough to think about. There's Coach Wood. He could teach this part.
I don't like the shrinks and the spread. It just makes me mad.
Yeah, they look the same.
I just want them to know it's getting closer to the x-axis or the y-axis.
Uh-huh. Yeah. Yeah. It's great fun.
I just did that 3 or 4 weeks ago, right?
Yeah. I said the ones that just had Math 3 should have a major. They've generally had a major advantage for the whole class so far. Yeah. Yeah, you really have to know your rules here because when you look at it, let's look at what happens here. Look at the C right here. This looks the same as what we just had for our vertical compression, right? It looks the same. In fact, we could, if we wanted to give some really difficult questions, we could ask you what vertical compression would be the same as a horizontal stretch. And you could have to figure that. That'd be a good question, wouldn't it? I should give it to him. So we can do this for either one. So this one looks like it's just been squashed down, right? But whenever we have a number on the inside of the parentheses, we need to be thinking about horizontally, okay? So now you think like an accordion, right? So if we take a graph and we, actually I shouldn't do 0.5. Do a number bigger than 1 is the one we're doing here. We're thinking about taking that graph, and in this case, if we're thinking about width, multiplying by a big number squashed it in, right? It's skinnier, right? So this is going to be a horizontal compression. I try to always teach that anything inside of the parentheses, number one, it's going to be x-axis, right? It's going to be horizontal compression, or it's going to be moving left or right. And everything's always backwards inside of the parentheses. So if a number is inside of the parentheses, it's going to do the opposite of what you think it should do. So if you have a big number, and when I say big number, I just mean like a number bigger than 1. If you have a big number, it's actually a compression. It makes it smaller, right? Yes? So if you think about like what's happening here, like if you had a table for that, like if you had a table just for x squared, like -2 would be 4, and -1 would be 1, and 0 would be 0, 1 would be 1, and 2 would be 4, right? So if you think like you're, starting from that basic function, whenever you multiply by a number right there next to the x, what's happening is whatever number your x was is now, like if we're multiplying by 2, it'd be twice as big, right? So like, in this case we got 3.8, so let me put another table here. So like, if I do that same table, right, so these same things. So whenever you plug it into the function, now you're taking that x and you're multiplying it by, let me make it a whole number so it's easier to do, multiplying it by 3. So like if I take these x coordinates and I multiply them by 3, this would be 6, and then this would be -3. That one would still be 0. This one would be, why is this not working? What is it? Horizontal compression. I guess it sure was. My explanation's gone horribly wrong here. Ignore what I'm telling you about the tables. Let me rethink that, because I need to think about it again on explaining why that works. I know it, but I think I've got something backwards there. Oh, I know why. We'll talk about it in a second. Let me teach you one more thing and then I'll show you. I got my factors off is the reason why. So so we'll talk about that in the notes just in a little bit, and I'll show you again so that it works. So that's a horizontal compression. If I use a number between 0 and 1, it actually makes it wider. It is a horizontal expansion. So here, so I'll have a horizontal expansion. And the last one that we're going to look at is kind of weird, and it's going to look like it doesn't do anything here if I just do it for this problem. So if I do ABS in Desmos is going to be your absolute value. So right now it looks like if I take the absolute value of this x squared, it does nothing, right? Looks like it doesn't do anything at all. Let me change my equation to be x squared minus 9. So now, if this is the function I'm starting with here, then if I take the absolute value of that function, this here is what I end up with. Okay? So what the absolute value does, remember if we're talking about absolute values, like if I take the absolute value of -7, what do I get? 7, right? I had a teacher that just called it the washing machine. It just washes away the negatives, right? Because some kids want to say it makes negative, like absolute value of 7 is still just 7, right? It's not negative 7. So if you put clean clothes in the washing machine, it washes them and then they just still stay clean. If you put dirty clothes, like negative, in the washing machine, it washes it away. And then no matter what, you come out with clean clothes, hopefully, unless it's like the laundry at my house where there are mysterious stains on everything that comes through. Well, not everything, but anything that's smaller than a size 10 in child's clothes. They have strange stains on everything. But they should come out clean in the end, right? If I was better at doing laundry, maybe they would. So what happens here is all of the negative parts are reflected over the x-axis, but only the negative parts, right? So, like if we think about what that looks like this part of the graph was positive, so it just stayed where it was at, and this part of the graph was also positive. It was above the x-axis, so it just stayed where it was at. But when you got down to this negative part, it had to be flipped over the x-axis. So if we have absolute value, and the absolute value is a transformation, not the graph we're starting with, but a transformation. And when we get a little further, I'll show you how to tell the difference. Then it's going to reflect the negative parts over the x-axis. It makes kind of cool graphs, as long as you got something that is makes kind of cool graphs as long as you got something that was below the x-axis at first. It didn't look cool whenever we just had x squared, right? If we had like x to the third, it would make sort of a weird graph there. If you had something like square root of x, it wouldn't do anything to it. But if you had square root of x minus 5, now it would. So you take that negative part and flip it back over the x-axis. So it makes kind of strange looking graphs. There. All right, questions? All right, let's start looking at, we're going to look at compressions and expansions just in a little more detail to talk about it. And then I'll try to re-explain what I was explaining a little bit earlier correctly. But let's do this first. So when a number is inside the parentheses, either adding it or multiplying it, the graph will behave in an opposite manner than you think it should. For example, positive number added to the x will make it move in the left or negative direction. Also, a larger coefficient in front of the x-axis will result in a horizontal compression, and a smaller coefficient between 0 and 1 is a horizontal expansion. And so I've got these pictures here to kind of help you think about vertical expansion and compression. I like this in Word better than other programs because Word will let you actually do this. So like if I'm thinking about vertical expansion, it's like we're grabbing that y-axis and we're stretching it out, right? So like I'm grabbing this right here and I'm stretching it along the y-axis, right? So that's what it's going to look like whenever we have that vertical expansion. Makes it taller and skinnier. Whereas if I have a vertical compression, it's like I'm taking that y-axis and I'm squishing it down. So if I take this and I squish it, it makes it look like it's sort of wider and shorter. Horizontal expansion is the same thing, but we're grabbing the x-axis instead of the y-axis. So it would be like this. If you took the graph for an expansion and you stretch it out, it's like an accordion that you're stretching out, making bigger. And then for our compression, it would be like squeezing our accordion in, making it smaller. And like I said, these are hard to tell from the graph because a horizontal expansion looks the same as a vertical horizontal compression looks the same as a vertical expansion on most graphs. So in fact, we could do one or the other and have them actually be exactly the same. It would be a little bit of a tougher problem, so just looking at the graphs, it's hard to tell whether it's vertical or horizontal. So that's why it's important that we know our rules for our equations. Factors are important here, and this is what I had wrong whenever I was trying to do my table, and it went terribly wrong. So, for vertical expansions or compressions, this is whenever our number is on the outside of the parentheses. We say that f is expanded or compressed vertically by a factor of whatever number is there. So if it was a 7, it'd be expanded by a factor of 7. If it is a compression, it would be compressed by a factor of 1/2 or whatever. So it's just whatever number you have there. Horizontal expansions and compressions are like everything inside the parentheses, they're backwards. So we would say if we have an A that's in here, A just being any number, 2, 7, 9, 43, 1/2, whatever. It would be expanded or compressed by a factor of 1 over A. Okay, you might want to make yourself a note here. Expansions. It does not matter if it is vertical or horizontal. Your factor should be greater than 1. So it should be bigger than 1. And if you have compression, your factor should be between 0 and 1. So actually, let me write it like this. 0 is less than the factor. Less than 1. So the number in the equation might not be, but the factor that you're talking about should always be a small number if it's a compression, a large number if it's an expansion. All right, so let's look at some examples. This is what we're going to kind of be working with today. Your assignment is going to be another matching activity, so you're going to kind of have to know what's going on here, although I do need to fix it because the link was not working. You weren't supposed to do it yesterday, but Ms. Hendrick did tell me the link wasn't working, and I need to fix that. So if I have a y equals x plus 3 squared minus 2, what type of function am I dealing with here? What's the parent function? Quadratic. And Maddox, tell me one thing that has happened to this graph. So our parent would just be y equals x squared, meaning I got that plus 3 that's different and this minus 2 that's different. All right, very good. So that minus 2 is going to shift it down 2. Braden, what else has happened to this? Very good. also to the left 3. Remember, on the inside of the parentheses, it's backwards. So if you see a plus 3, it actually goes in the negative direction, which would be left 3. All right. Jackson, what type of function have we got for number 2? Cubic. And so we have a number, this time it is multiplied on the inside of the parentheses. So let's start vertical or horizontal. If we're on the inside of the parentheses, is that going to be vertical or horizontal? And you're welcome to look back at your notes if you need to, Jackson. Yeah. At this point. It is not. It is going to be horizontal. So, horizontal. So, inside the parentheses is always the x-axis, which is horizontal. Which means if you're adding or subtracting on the inside, it moves it left or right. Usually kids are better at that. But if you're, the stretches and shrinks are what's really hard. If it's inside, it's still x-axis, so it's horizontal. You're stretching horizontally there. Then everything on the inside is backwards. So if you have a big number, and when I use that generic term big number, I mean something bigger than 1. So if you have a big number, it's actually going to do the opposite of make it big. It's going to make it small. So this is going to be a horizontal compression. By a factor of, so if it is a compression, it's horizontal inside of the parentheses, we got to do 1 over that number there that we see in the parentheses, so 1 over 3. And all compressions should have a small number, right? So it's a big number in the equation, but it's a small number when you're talking about the factor. So if we flip back over to Desmos real quick, let me show you what I was doing wrong on that last one. So we were looking at x squared, and let me get rid of that. So if I take the table like I had, ooh, no negative, sorry. Okay. So, if I have this table right here, this is what we start with. And I want to see what happens whenever I have 3x, like this. So if I got that, not to the third, second. I've got that inside. So if I take that table, just like it was. So if I take all of my x coordinates, and so what I was doing wrong earlier, Hallie, when I was trying to explain this, is I multiplied all my x coordinates by 3. But our factor is actually 1 over 3, right? So if I multiplied everything by 1/3, so basically just it's going to be divided by 3 right there. 0 divided by 3 is still 0. It's going to take those and it's actually going to like squish them in. Because for us to have like -2, since it's being multiplied by 3 here, it's actually, you're going to have like 1/3 of what you would to get that same result as you would have up here. The factor was what I had wrong there. I was multiplying by 3 where I should have done the opposite there. So let's move on. All right. Here we have a square root. All right. Blaine, tell me one thing that's going to happen to that square root function. Yes, very good. That +3 right there is going to cause it to go left 3. All right. Here, the square root symbol acts like your parentheses, even though there aren't any parentheses there. All right, Caitlin, what else is going to happen to it? Very good. Sometimes this throws kids off right here that the 5 is out front, but if you wanted, you could move it over here as a +5, like that. So that means there's also one more transformation. Connor, what else is happening? That negative right there is going to reflect over the x-axis. Okay, questions? Up here. All right, so for the next one, we've got a cubic. Bronwyn, what's one thing that's going to happen to it? Not left 2. You are correct. So whenever you don't see parentheses, if it's a square root, then put parentheses like right here. That square root counts as the parentheses. Here on these two, we actually had parentheses. If you don't see parentheses at all, it's like it's just around the x. There's nothing inside of those parentheses. So this 2 right here is multiplied. When you're multiplying, that's going to be expansions or compressions. And if it's on the outside, it's vertical. And everything on the outside of the parentheses works in the direction it should. So if you have a big number like 2, 2 is bigger than 1, it's going to make the graph bigger, so it's going to be expansion. And it's going to be by a factor of 2. You don't do anything special with it. It's just whatever number it is. So, Grace, what's the -4 going to do here? Down 4. Good. Okay. The next one we have here is a rational. And for a rational function, it is helpful to think of it like this. So you want to think of it like the denominator is where your parentheses are. It also may be helpful to think of it like this. 3 times 1 over x plus 2. Because this number here that's in the numerator, like if I did this, that would be like 3 over 1. If I multiplied it back together, I get the same thing that I started with. So this is a 3 that's being multiplied, even though it kind of doesn't look like it because it's in a fraction, right? So if we have a 3 that's being multiplied, it's on the outside of the parentheses. Braden, what's that going to give us? The 3. It is actually, it's going to be vertical. And it is vertical because it's on the outside of the parentheses. And if it's on the outside, it acts like it should. So if I have a 3, which is a big, what we're going to call a big number because it's bigger than 1, it's going to make the graph bigger, right? So it's going to be expansion. And so that would be by a factor of 3. And then, Reese, what's that plus 2 going to do to the graph? Not down. It's inside of the parentheses, not up. Anything inside is x-axis. It's horizontal. So it's going to go left or right. In this case, it's going to be left 2. So anything inside the parentheses is either moving it left or right or stretching it horizontally, but it's all horizontal if it's inside the parentheses. Outside the parentheses, that's when we move up or down and have vertical. Okay. Number 6, we would have parentheses right here. And so for this one, let's see, Connor, so we got square root. What's going to happen to it? Right, 4. It is reflected over the x-axis. That is our negative that we're looking at right there. Vertical compression by factor of 1/2, just the number that's there. So I really like that Connor treated that negative separate from his 1/2. And you need to do that every time because negatives are going to flip, right? So we treat the negative separate from the 1/2. So you notice when we were doing expansions and compressions, I never dealt with any negative numbers, right? Because if it's negative, that is flipping the graph. So it's separate from the number. This is on the outside of the parentheses, so we know it's vertical, right? Anything on the outside is either going to shift up and down vertically or stretch up and down vertically. And then we just use that factor. We get 1/2. Yes?
So why does it reflect to the x-axis if anything on the outside is the line?
So think about what happens if you flip something over the x-axis. So x is where you're flipping, but like let's say if we're above the x-axis and then we take everything and move it below, which coordinates are going to change? They're going to be your y coordinates, right? So it is, you're flipping it upside down, like vertically, but the line is that you're flipping over is horizontal. So I understand the confusion there. But mostly it's because like the x-axis is a y equals line, right? So it's dealing with your y coordinates even though it is the x-axis you're flipping over. Good question. All right, and we are basically out of time, so those last couple I'm not going to get to. I need to look at this Desmos classroom and redo it so that it's working for you guys. So if you guys want to go ahead and pack up and wipe off your desk, I'm going to get this working and I'll show you what it looks like here. Have I got a class for, I don't think I have a class for you guys. Okay. Copy. All right. No. All right. All right, I'm hoping this is going to work, even though I've got to go over here. Where's it at? Oh, there it is. No, that's trig. It's not it. Where's it at? What's the name of it? Functions, card sort. Is that what I called this? Oh, there it is. Okay. So assign that to you guys. Assign. Okay, so can somebody, let me publish it. Let me save this. Can somebody go into Canvas real quick and click on that link and just make sure it takes you to Desmos classroom? If anybody, well, I don't know, go do it on your phone. Is it? Yeah, if you don't mind. Blaine's going to do it for you. Thank you, guys. And if it's, I'll have this working where the link will work to take you to what you're supposed to do. Is it working? Yes, that one is homework. Yes, that very last one. Yeah. Yeah. Okay, it's got it on there. Okay, good. All right, good. Alright, I'm gonna go fill up my water. I'll be right back. Oh, see where you can go. Straight up. That's what your plan is. Well, it's at 0 right now, so anything will help you, but if you make 20, it's not gonna help you much.
We don't want to do that. What is that small bag?
Wesley.
What's up, brother? The animated, yeah. Like, comics that turn over like cards.
Alright, go ahead and put your phones up for me. Grab your calculators. And Jada, you're going to go down to Coach Swisher's room to finish that test. So what,
It's on the second floor, right? I forgot. Like, it's on the third floor.
no, he's on this. Yeah, he's on this floor. And make sure you leave your phone here. Let me get you the access code for the second part too.
That's how you're staying now, right? Like, you're back.
Lord willing,
Thank God.
till we get sick again. Our immune systems are not great.
Let's not get out again.
Or till the next time Henry gets quarantined, because the rest of us are.
I need you to stay here.
The rest of us can't get quarantined for 90 days, but Henry never get it. So, hopefully he won't get quarantined.
And that's the youngest one.
Yeah. But, I mean, he was, like, in the house, all around us,
I think that's something.
Like, that should count for something, I
Because he has
think.
a strong immune system.
Usually not, but maybe he had already had it or we not known it or
Some people
something.
are carrier.
Yeah, I think some people just don't get it and then like, or get it and they're not sick enough for you to ever know they really had it, so.
That's how I was. Because I wasn't even sick. I got one with my parents got one and they were both positive. And there were no symptoms. There hadn't been symptoms the first time, and I still had it.
Yeah. All right.
I need to the calculator.
Yes, because now the second part, well, active, right? The second part is not calculator active, so don't use it on that. Yeah, you can just give it to him. But you need to go ahead and finish the other part you started. And make sure you write down your work for it. So you can go ahead
Couple of things today. We do have a broadcast today, so it will begin immediately following announcements. Have your TVs turned on. Ready for that? We'll begin immediately following announcements today.
Yes.
Good luck to our swimmers, swim team. We have a lot of swimmers that are going to regionals today. They will be competing this evening in Greensboro, both men's and women's teams. Good luck to all the swimmers. I know you're going to do well. For our students and teachers, a reminder, if you are eating lunch or breakfast in classrooms, we ask that you please remember to put your trays and food trash, in the trash cans of the hall. Don't put those in the trash cans in the classrooms. Again, food trays, food scraps, please put those into the trash cans in the hall when you get finished. We do have pledge this morning. Cadet Van Horn will lead us in our pledge.
Please stand for the Pledge of the United States. Attention, salute, pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
We didn't stand for pledge, but we
Thank you. Have a great day. As always, today is a great